In this lesson, we'll consider parallel RLC circuits and discuss how they can be applied as filters. We already know how to treat parallel circuits with AC sources by converting the impedances to admittances, the reactances to susceptances, and the resistance to conductance. We'll be using those concepts here in this lesson, so it's a good idea to go back and review those concepts before proceeding. The simplest and yet most common type of parallel circuit is called the tank circuit. It is composed of an inductor and a capacitor arranged parallel to each other as shown. It is called the tank circuit because energy is transferred and exchanged between the inductor and the capacitor with no loss, ideally. The exchange happens on alternate half cycles. When the capacitor charges, the inductor loses energy, and when the capacitor discharges, the inductor gains back the energy or energizes. As in the series circuit, the resonant frequency also has the same expression and occurs when the inductive reactance is equal to the capacitive reactance. When X sub L is equal to X sub C, the currents through the inductor and the capacitor are equal in magnitude. Since those two reactances are always out of phase with each other by 180 degrees, then at resonance, the total current is zero. Let's consider this circuit as an example. Furthermore, let's consider the ideal case and ignore the resistance for now. The admittance is given by the following equation, where G is equal to 1 over R, B sub L is equal to 1 over X sub L, and B sub C is equal to 1 over X sub C, and Y is equal to 1 over Z. Since we are ignoring R for now, we also ignore G so that the admittance is purely due to the susceptances. The main graph shows the impedance curve versus the frequency, and the inset shows the current response to the frequency. At low frequencies, below the resonant frequencies, the capacitive reactance is greater than the inductive reactance, so that most of the current passes through the inductor. At the resonant frequencies, the impedance is infinite. It follows that the total current is zero, since the currents are equal. At frequencies above the resonant frequency, the inductive reactance is greater than the capacitive reactance. Thus, most of the current passes through the capacitor. Now let's consider the non-ideal case when there is resistance due to the winding of the coil. In this example, R is equal to 20 ohms. Since the resistor and the inductor are in series, we can solve for the quality factor as shown. These equations assume no loading effect from the input resistance due to the source or an external load resistance. We can convert the non-ideal tank circuit to its parallel RLC equivalent using the following equations. From the equation, you can easily verify that when Q is equal to or greater than 10, the equivalent inductance is equal to the original inductance. Why did we need the conversion from the non-ideal tank circuit to the parallel RLC circuit? In the parallel RLC equation, we have the ideal tank circuit in parallel with our PEQ. We already know how to interpret the ideal tank circuit. At resonance, the impedance of this tank circuit is infinite. Thus, the total impedance of the circuit is equal to the equivalent parallel resistance of our PEQ and the tank impedance. Since the tank impedance is infinite, the total impedance of the circuit is just equal to the expression above as derived previously. Notice that the tank circuit's inductive reactance change. Since the inductance changed by a factor of Q squared plus 1 over Q squared, what would happen to the resonant frequency then? In other words, what is the resonant frequency in the non-ideal tank circuit? The definition of resonance is when the inductive reactance is equal to the capacitive reactance. Since we are now solving for the equivalent inductive reactance, we can rewrite the equation as so and derive the resonance frequency as shown. Notice that if Q is greater than or equal to 10, then we revert back to our original expression for the resonant frequency. Let's now investigate how the tank circuit can be used as a filter. To allow us to be able to graph the results, I use R equals 20 kiloohms, L equals 50 millihenry, and C equals 47 picofarad. This gives us a resonant frequency at 104 kiloohms. In this configuration, when the output voltage is taken across the tank circuit, the circuit acts as a bandpass filter. The circuit is enclosed inside the magenta rectangle, and the result of the simulation represented by the magenta solid line. When the output voltage is taken across the resistor, the circuit acts as a bandstop filter. The circuit is enclosed inside the blue rectangle, and the result of the simulation is represented by a blue solid line. In this case, the bandwidth is about 2 kiloohms. It's very useful to some applications. What would happen if we added other resistances, such as the internal resistance of the source, the winding resistance of the coil of the inductor, and the load resistance? We already know what to do with the winding resistance of the coil. We convert this portion of the circuit to a parallel RLC circuit and solve for the equivalent RP and the new equivalent inductor. This new RP equivalent is then parallel to the load resistance. We can then solve for its equivalent resistance. In the figure, it is represented as RP total. RS and RP total forms a resistor voltage divider. Thus, the tank series sees a reduced input voltage. This reduces the output voltage and consequently increases the bandwidth. Remember that to get L equivalent, L is multiplied by a factor of Q squared plus 1 over Q squared, and thus L equivalent is actually greater than L. This means that XL increases and the total impedance also increases. This implies that at both sides of the resonance frequency, where XL is present, the impedance increases as well, which means a reduced current and a reduced voltage. This consequently results to a larger bandwidth. One typical application is a tuned amplifier. An amplifier is any circuit or device that increases the input signal. All signals that are taken as input by the amplifier are increased, including noise. Thus, if you use the tank circuit, you can improve the selectivity and decrease the bandwidth. A variable capacitor is typically included to allow for the tuning over a range of input frequencies so that the desired frequency can be selected. One such application is in your radio. The signal carried by the electromagnetic waves are detected by your radio through the antenna. This signal is very weak and needs to be amplified. It also contains a lot of unwanted signal, which is why you need the tank circuit to act as the bandpass filter. When you dial the knob, you actually change the value of the capacitance in order to tune to the station you want to listen to. A slightly more complicated circuit employed by your radio receivers is this super heterodyne AM radio broadcast receiver. Let's say that you want to listen to a radio station at a frequency of 600 kHz. The radio station sends out that specific frequency uniquely assigned to it. The transmitted signal, that is, the music or whatever audio, is carried by this 600 kHz frequency as an envelope. In the figure, it is represented by the border lines enclosing the main signal. While the antenna acts as some sort of filter, it still receives a large range of electromagnetic frequencies. The tank circuit filters out all the unwanted signal but keeps the 600 kHz signal. In this configuration, you have two tank circuits in series, both operating at 600 kHz. Such dual series filter is called a second-order filter. It improves the selectivity by increasing the slope of the signal. For example, filters such as those we have been studying is a first-order filter. It has a slope of 20 decibels per decade in the gain plot. Adding a second filter makes it a second-order filter and increases the slope by twice as much to 40 decibels per decade. At the output of the second-order filter, the signal is delivered to the mixer, where a 455 kHz signal more than the frequency of the input signal is added. This is why you have a 1055 kHz signal, since 600 kHz plus 455 kHz is 1055. So you add the 1055 kHz signal to the 600 kHz signal. This is the local oscillator signal local to your device. The 600 kHz signal is essentially removed through a process called heterodyning or beating. The 455 kHz local signal is the standard intermediate frequency for all receivers. This is then further amplified and filtered out at the resonant frequency of 455 kHz. The 455 kHz is then removed by the audio detector, leaving only the envelope, which is your audio signal. It's finally further amplified and sent to your speakers. Another application of filters is your crossover network. This network uses filters to separate the audio frequency bands, creating the variety and richness of sounds that you hear coming out of a set of speakers. The woofer employs a low-pass filter. The tweeter employs a high-pass filter. The mid-range speaker employs a band-pass filter, producing the frequencies not covered by the woofer and the tweeter. I hope you've come to appreciate all that we've covered from the beginning of the semester. We've already covered a whole lot from phasers to their applications as filters. When you've done studying all of the topics, you should now be ready for your first exam. But just before that, we'll discuss a few examples pertaining to the frequency responses in series and parallel AC circuits. You'll then take on quiz number 4 before gaining access to the first exam. There's still plenty of time to ask questions and talk about what you still need to learn. So please don't hesitate to ask and visit me during our consultation hours. Good luck and see you in the future lessons.